general relativity postulates that spacetime is a pseudo-Riemannian manifold with Lorentzian signature, such that it obeys special relativity in the Einstein field equations, with the curvature mathematically defined by the stress-energy-momentum tensor and dark energy. Ish. Confused? Let's break it down. Beginning with special relativity, which can be summarized with two postulates. First, there is no preferred reference frame. In other words, the law of physics apply in all inertial reference frames, in which an object at rest remains at rest and an object in motion continues its motion without experiencing any net force. Therefore, although quantities may differ, physics behaves the same, whether you're an individual standing on a platform or a passenger on a train. The second postulate states that the speed of light is constant in any such inertial reference frame. Therefore, if this train were to have headlights, the speed of the light measured by the passenger on the moving train and the observer on the platform are identical. This may seem counterintuitive. Imagine a flashlight is moving at half the speed of light, c/2, and is turned on, shooting light photons outward at light speed, c. To an observer at rest, if the flashlight has a speed c/2, Newtonian physics tells us that relative to this observer, the photons must be traveling at c, the photon's own speed, plus c/2, the speed of the flashlight. But relative to the person holding the flashlight, the photons just have speed c. According to this second postulate, the speed of light of the photon is absolute, meaning it is the other physical factors that are variable, making up for this perceived difference in speed, namely space and time. Under these laws, many quantities we hold constant under classical Newtonian physics now become relativistic, in other words, dependent on the frame of reference and its motion. Rather than being separate, time becomes a fourth physical dimension that forms a geometry. So what does spacetime look like? It cannot simply be curved and warped in any which way. This is where we introduce its Lorentzian signature. In one reference frame, the behavior of physical quantities in another reference frame can be mathematically derived using transformations known as Lorentz transformations, stemming from special relativity. Moreover, mathematicians call this specific geometry a pseudo-Riemannian manifold, which essentially means locally flat, a smooth geometry without kinks or knots. All of this is to say, there are rules that govern the relationship of different objects at different locations in spacetime, together forming the fabric of spacetime. This fabric, which all entities exist on and are influenced by, can be curved and stretched. This observed effect on objects under the warp of spacetime is known as general relativity. So let's summarize what we've learned so far. General relativity is the effect of the curvature of spacetime to not just any shape, but a specific geometry defined by mathematical transformations, known as Lorentz transformations, and it resembles a pseudo-Riemannian manifold, smooth curves and locally flat. But we are still missing a piece. What exactly is this effect? What does this fabric of spacetime actually look like in our universe? What affects the warp of this fabric? What happens to this fabric in the presence of matter, like our Earth, the Sun, and Moon? Mathematically, Einstein found that the curvature of spacetime can be characterized with 10 nonlinear differential equations, known as Einstein's field equations. For simplicity, they can be summarized by the following parent formula. The left-hand side quantitatively describes the deviation of spacetime from flatness, and how much space is stretched, including its overall structure. In addition, the third term is a cosmological constant, which describes the intrinsic energy density of empty space and the absence of mass, known as dark energy. The right-hand side is composed of just one important term, the stress-energy-momentum tensor, or the density of mass, momentum, and energy at a given point in space. Thus, the curvature of spacetime is dependent on the density of mass and energy and the presence of dark energy, where a large density leads to a greater curvature and thus a greater influence on an object. Keep in mind, these diagrams of spacetime are 2D simplifications, as representing the warp of spacetime in higher dimensions is a non-trivial task. At this point, we can begin to see what the effect of a warp in spacetime is analogous to. For greater clarity, let us depict the warp of spacetime with the Earth, Sun, and the Moon. The relatively large mass of the Sun creates a warp in spacetime. When the Earth is placed in proximity to the Sun, its motion of free fall in spacetime, known as a geodesic, would be directly into it. However, given a velocity such that it is able to maintain a variable distance, it becomes trapped in an orbital pattern. Since the Earth too has a mass, it too warps the fabric of spacetime around it. As such, with the Moon in close proximity, it becomes trapped in an orbital pattern around the Earth, one that is also influenced by the warp of the Sun. The Moon also has a mass. Its warp on spacetime causes the wiggly motion of the Earth's orbit and even the ocean's tides. Therefore, the effect we observe is a gravitational effect, which is a product of the warp in spacetime, that, as Einstein's field equations relate, result from differing mass, energy, and momentum densities in our universe and dark energy. This theory of general relativity refines Newton's law of universal gravitation, providing a reason that gravity is not just an inherent force of all matter, but a geometric property of the curvature of spacetime. In conclusion, piecing together the parts, general relativity characterizes gravitational effect as a geometric property of warps in spacetime, which is not randomly shaped, but rather is a pseudo-Riemannian manifold, meaning smooth and locally flat, with Lorentzian signature, meaning it obeys special relativity, where physical quantities such as time can be transformed into different frames of reference using mathematical transformations. And as Einstein's field equations relate, these warps are caused by the mass, energy, momentum densities at a given point and interactions with dark matter. This theory of general relativity provides the basis to modern physics and offers fundamental insight not only into the physical phenomena we observe, but predictions about the universe's origins, development, and possible futures.